Okay, so good morning. Let me just briefly recap what we had last time. So basically last time we stopped by saying that these class of functions that we defined, let me just write down the definition once more, just so you remember the definition of everything. We had these class of functions which we said appear when you do loop computations with something called multiple polylogarithms, and we said they form a Hopf algebra. As a result, that goes back to Goncharov. And while I gave you the way how to construct a coproduct, but we're not going to recall it here. I'm just going to give you two simplest examples. So at weight 1, I remind you that weight is the number n of integrations. The coproduct is essentially trivial. It just tells you that the log cannot be decomposed. There's no non-trivial way of decomposing a log. And for these functions Li(n), there's a closed formula for arbitrary n. That allows you to write down the coproduct. Okay? That's pretty much where we stopped last time. Are there questions about that before we go on? No? Okay, so from this last line, I can infer something. Namely, remember that we said that Li(n), evaluated at 1, is the Riemann zeta function, evaluated at that integer n. So from this, I immediately get that delta of zeta n is 1 tensor zeta n plus zeta n tensor 1. Okay, why? Well, I put z equals 1 in here, so this term gives me this. And here you see I have log of 1. So all the terms in the sum vanish except k equals 0. And then I have here n minus 0, so again zeta n. Okay? Now this is bad. This is really, really bad. Why? Yeah. There's a problem with n equals 2 now. The problem is the following. You know that all the even zetas are proportional to powers of pi. For example, zeta 2 is pi squared over 6. And zeta 4 is pi to the 4 divided by 90, which I can write as 2/5 zeta 2 squared. Okay? But then, let me compute delta of zeta 4. Well, that is 2/5 delta of zeta 2 squared. And that is 2/5 1 tensor zeta 2 squared plus zeta 2 squared tensor 1 plus 2 times zeta 2 tensor zeta 2. And so I get 1 tensor zeta 4 plus zeta 4 tensor 1 plus 4/5 zeta 2 tensor zeta 2. Okay? And that's a problem because that's a contradiction with what I wrote down here. Okay? So there's a contradiction in there. So how can you solve it? Well, there's one obvious solution, which is the one that you find actually in Goncharov's paper. And actually, I've been lying to you. Well, this statement is true, but I know I said that this vector space A that we defined is a Hopf algebra, because actually it is not. But this Hopf algebra is something which you can call H, which is defined, if you want, as A modulo zeta 2. So zeta 2 is 0, essentially. Now, of course, then there's no contradiction because you get 0 equals 0. It's, of course, not quite satisfactory, okay? Yeah?
Does zeta n belong to the vector space?
I defined it as Vn, so it's a polylog function. And remember that I defined it as the vector space that's being defined over the rational numbers. If you believe, as everybody does, but there's no proof that this thing is transcendental, then it is, if you want, a non-trivial element. It's not a scalar. Okay? Maybe you remember the question that we had at discussion session in the evening. Why was it the rational numbers, not the reals? Well, if I had taken the reals, then this thing would be scalar, and it would be trivial.
Excuse me. So this peculiarity only appears with zeta 2? Doesn't it appear with any other zetas?
No, of course. I mean, then, of course, also with zeta 4 and zeta 6, I mean, all the even ones. Okay?
They're all given in terms of the zeta 2.
All the even zetas are proportional to powers of zeta 2. Or pi, if you want. So you can even refine it. You can immediately say that the same problem appears with I pi, log minus 1, okay? Because zeta 2 is I pi squared, well, proportional to I pi squared, so the same problem appears there. So here, well, it's okay. It's the ideal generated by zeta 2. So it's the same as zeta 2 times A here. Okay, and actually I can refine it. Let me put I pi. Okay, because of the argument I just said. So H is my original algebra divided by the ideal generated by I pi, and actually this thing is a Hopf algebra. So that is the actual statement. It's, of course, not very, very nice and not very useful. Well, it's useful from the formal point of view, whenever I want to do computations, and I don't get my zeta 2s right, and I've not achieved that much.
In this way, you get rid of cuts, of logarithm cuts.
Yes. I will put them back in a second. But you're right. This essentially tells you that you have to, the Hopf algebra, in principle, does not know about the cuts. Okay. I can kind of trivially invert this relation and say that A is actually, let me first write it and then. It's essentially the same. Saying that A is A mod I pi, same as saying that A is this. Why? Well, here I said, okay, I put to zeros all pi's. So I can say, well, any element of A, I can write it as something where I have no pi's, and I just dumped all the pi's into the coefficients. It's the same statement. We say pi, the difference is, but is it clear or should I explain it in more detail? But it's the same. The difference comes from if I write 2 times I pi times log x. I can either say this thing is in A times 2, or I say this thing is a polynomial in I pi, and the second one is actually in H. It's the same thing.
Why do you write Q? Q of I pi is the ring of a polynomial.
It's the polynomials in I pi.
Yes, but with rational coefficients.
Yes. And I pi is transcendental over Q, so this thing makes really sense. It's a non-trivial ring. So, with that, you get to something that goes back to Brown, roughly. That actually, if I define now delta of I pi as R pi tensor 1, so on these objects, I define delta like this, and at these objects, I define it in the way I had defined it over there, then it all works. The actual statement is that A is not a Hopf algebra, but A is what is called a co-module. Now, the technical word co-module is irrelevant. It basically just A behaves as if it was a Hopf algebra with a special rule that pi behaves in this weird way. So you can still think of it as a Hopf algebra. Naively, you would expect I pi tensor 1 plus 1 tensor I pi, just as for the logarithm, okay? Because I pi is log minus 1. That also means that now, in a co-module, actually, delta goes now from A to A tensor H. Okay, but I have to kill the second term, which is 1 plus I pi. So I have to project out pi's in the second factor. And once I do that, it all works. So then the non-trivial conjecture is all functional equations for multiple polylogs with, and put this in quotation in parentheses, with rational functions as arguments, follow from delta. And I will give you an example by what that means. So all the relations among these functions are just encoded in this algebra. So remember that at the very beginning I said that actually these relations among these functions are in the end just some concrete realization of some abstract algebraic structure. Well, that's the same as saying this. There's an overarching abstract algebraic structure which controls all the relations among these integrals, which in a concrete realization come about as change of variables and so on.
This is stronger than demanding that it's a graded.
This is much stronger, yeah. This contains the grading.
This contains the grading.
Yeah.
But even the grading is conjecture.
Yeah. The grading is not a conjecture. If this conjecture is false, the grading conjecture could still be true. But since delta itself is graded, this means that the grading, there cannot be relations among different weights. Okay, so let's look at a quick example, a simple one. Because if you do it in practice, things can go easily out of hand and you need a computer. So let me do the following. Let me take E1 of 1 over x, which is log 1 minus 1 over x. Let me tell you that x, for example, is positive, even bigger than 1, say. Is it? Sorry, less than, positive and less than 1, sorry. If it's positive and less than 1, then you see that this log develops an imaginary part. And let me fix the branch by requiring that log minus x is actually log x minus a pi. I could choose another branch, but let me fix it this way. I have to fix it somehow. And of course, this thing you can easily check is actually log 1 minus x minus log minus x. Yep. So that log 1 minus x minus log x plus I pi. Okay? Now, what is the corresponding formula for Li2 of x? I'm not claiming to do something new. You can find this relation on Wikipedia, but how can you get it? Well, if I act with delta, I get 3 terms. Okay, you use the formula that I gave you for the delta of Lien, and you get the following identity. Right, the following relation. Now, the first 2 terms don't tell me anything new. They just contain the same information as the original function, okay? So those are the 2 trivial ways of decomposing that object. The non-trivial bit is this one. That one has 2 factors, each of which is lower weight. So I can assume that I know already what's going on. Okay? Particularly, I know everything about these objects. So if I plug in the relations I had here, I get log 1 minus x minus log x plus I pi tensor minus log x. Now I expand it out. I get log 1 minus x tensor log x with, and I missed the minus sign here somewhere. At the very beginning, here. D1 is minus log. So you have to, the signs here are reversed. Sorry for that. Plus, minus. And then I get a plus here. That's correct. Minus log x tensor log x plus I pi tensor log x. Now this thing is the same as this essentially. This is minus Li1 of x. The dish thing actually comes from minus Li2 of x. This thing you can check comes from 1/2 log square x. And this thing comes from I pi log x. And note one thing. Here it is very important that I had this definition, because you see the I pi only appears in the first factor. It does not appear symmetrized. If I didn't have this rule, it wouldn't work. Okay? So from this I can conclude that essentially under, well, this thing is minus Li2 of x plus 1/2 log square x plus I pi log x. Is that all? you see, I only looked at terms where I have weight 1 times weight 1. I projected out stuff. This projection might have a non-trivial kernel. And in particular, remember that we said that, well, the zetas, they are like 1 tensor something plus, well, zeta, the coproduct of zeta n is 1 tensor zeta n plus zeta n tensor 1. Okay? So the zetas get projected out. So in principle, I could add here any multiple of zeta 2, and I still have a valid identity. In principle, I have to add plus the kernel of whatever I projected out. In practice, it's mostly zetas. And indeed, when you put x equal to 1 in this relation, you get here zeta 2 equals minus zeta 2. This term vanishes, plus alpha zeta 2. So alpha is actually equal to 2. Okay? And you can check that you get indeed a relation. Well, that relation is well known. So that's nothing new. But of course, if you go to the more general case, the conjecture is that all the relations just come about in the same way. So you control essentially the whole space of functions. Okay? And note that nowhere did I use any kind of change of variables or integral representations or whatsoever. It's purely algebraic. It just follows from the underlying algebra. Okay? Are there questions?
Excuse me.
Yeah?
What happened with
Where?
the first two terms here on the left?
Yeah.
With the first two terms of the...
The first two terms, if you want, they don't contain anything new, okay? So delta, what it does, it tells you how you can decompose an object. One way to decompose an object is always not to decompose it at all. Okay? So whatever delta you compute, you will always have a term that is 1 tensor the object plus the object tensor 1. Okay, that does not contain any information. Just trivially mathematically there because there's one way to decompose an object. So that's why, if you want, I cannot look at it. Well, I can look at it, but if I know what happens in here, then I know the answer. Then I know the full function. Or equivalently, this term is precisely the information that is hidden in these two. But then again, if I know that term, then I also know the full answer. So the first two terms, if I put alpha equal to 2, the first two terms also come out right. But I cannot use them to derive the answer. Okay? More questions?
Yes, this kind of relation I can derive also by taking derivative of these expressions.
Of course.
And I get all this functional relation using just take a derivative, and then I take the nucleus of the integrals, and then it's very easy to get. And also I get also the Riemann function. So
of course.
How much is more powerful this method with respect to just
Well,
take derivatives? I mean,
imagine you go to the G's. I mean, this, I'm not claiming here that you couldn't do this in any other way. This identity was derived 300 years ago. Okay? But imagine you go to a function of weight 6 that depends on 5 variables. So you have to differentiate, possibly under the integral sign, integrate by parts, make sure that you don't miss any integration concepts that depend on the other 4 variables that you don't differentiate in, and so on. This is pure combinatorics. Of course, you can do everything via the differentiation. And we will see in a second that actually underlying this, there is a derivative. Okay? This is just a purely, for example, you can ask you the question, I give you g of x, 1 plus x, 1 over x, 1. Now differentiate with respect to x. How would you do it? Okay, you would write down the integral representation, then differentiate on the integral sign, you have to integrate by parts, it becomes very tedious. While in this way, it's purely combinatorics. You don't even need to know the integral representation, let alone differentiate with respect to x. Okay? But again, you could do it with in other ways. I'm not saying that it cannot be done in any other way. Okay?
Can I ask? Over here. If,
Where?
if
Yeah.
you are in a region where you don't have branch cuts,
Yeah.
then I guess Brown's prescription doesn't give you anything new because you don't have any IPIs appearing.
Well, you can have
And
zeta 2s.
You can have
Zeta 2s.
Zeta 2s. But these are not captured anyways, no? Or
No, for example, if you go to weight 3, you can have zeta 2 tensor log.
okay.
Those you capture.
Thanks.
Okay? Okay. So just 5 more minutes and then we're done with the mass. Then we go back to amplitudes. Okay. Let me just make some final comments about all this, about the mass part. The first comment is, well, our delta, what it did is a toggle function and returns the tensor product of two functions. Okay. Can I give a meaning to the left factor and the right factor? It turns out that the left factor, these are the discontinuities. Well, related to discontinuities, these ones are related to derivatives. And so this is what I meant before. So hidden under this is the differential structure of the whole thing. It's a combinatorial way to encode the differential structure. Okay? That's more precisely what it means is that if you take a discontinuity of a function and then the core product is the same as only taking the discontinuity in the first factor, and if you take the core product of the derivative of a function, it's the same as only differentiating in the rightmost factor. And this will be related to amplitudes in the end. Okay? As an exercise, you can work out something very simple. Put f equal E2 of x and check that these identities are satisfied. It's a simple exercise, but it's very instructive. But the only thing you should remember is that the leftmost factor captures the derivative, the rightmost factor captures, the leftmost factor captures the discontinuity, the rightmost factor captures the differential. And note the fact that we had for pi was always in the leftmost factor. You could say, why it was left, not right? Well, the reason is that. Okay. If for pi I had chosen delta of I pi equals 1 times I pi and put it into the right, then this would not have worked. So it's all interconnected. Okay, that's the first question, first comment. The second comment is that if I start with a function of weight 4, let's say 4, okay, then my core product allows me to decompose it into weight 3 and weight 1, weight 2 and weight 2, weight 1 and weight 3, and of course also weight 0 times weight 4 and weight 4 times weight 0. Okay? I can iterate it. This becomes, say, 1, 2, 1, 2, 1, 1. 2 I can decompose in this way, this one in this way, well, this one also here, and 1, 1, 2. Okay? Now remember that we said there's a unique way of iterating things. And last but not least, I can also iterate it by decomposing it maximally into weight 1 objects. Okay? For example, before we had the dialog and we got log 1 minus x tensor log x, then we stopped. Then we cannot go any further. I cannot decompose the log any further. So if I have a weight 4 object, for example, I can maximally get a tensor product of 4 logs. For weight 5, it would be tensor product of 5 logs, and so on. This is something people often call the symbol. By definition, the maximal iteration of delta. Okay? So that's basically when you have, well, let's give an example. For lead 2 of x, which we just had before, the decomposition into logs was log 1 minus x tensor log x, and then we stop because it's weight 2, and there was a minus sign. That thing is the symbol of lead 2. So the symbol of lead 2 is just the decomposition into logs. And because everything is just logs, people usually drop the log sign. Okay? Everything is anyhow logs, so you can just drop them. Okay? Those are just simple definitions. Are there questions before we move back to amplitudes? No? Okay. So then let's go back to amplitudes. Okay. Let's take an L loop integral. Let me denote the loop order by some superscript. And we work in dimensional regularization, so this thing is actually a Laurent series. Okay? And this thing is essentially a function of polylogs. It's a linear combination of polylogs. Now, what kind of questions can I ask? Well, the first question it says, you can try to answer, can I make any statement about the weight? Can any type of G appear in the answer? Okay, if I do a one-loop computation, can I get a leaf 5? Well, the conjecture is, it's really just a conjecture, the weight of the case coefficient in here is bounded from above by 2L plus K in 4 dimensions. If you change dimension, it will be different. And I think no one knows what the exact relation is in 6 or 8 dimensions. Okay? Something stronger happens in special QFTs, like, for example, n equals 4 super Young mills. There, the bound appears to be saturated. In n equals 4 super Young mills, actually, the weight seems to be exactly 2L plus K. Always. It's rather a miracle. It means that if you do, say, a one-loop computation in 4 dimensions, you get dialogues. Two-loop computation in 4 dimensions, you get D4, and so on. There's something known also from the spectrum of the anomalous dimensions. You only get a specific set of zetas at every order. Okay, it's the same statement, but it also holds for it appears to hold also for amplitudes and for correlation functions and Wilson loops and other things. Okay, so there seems to be kind of a grading on the integrals themselves. Okay. Last but not least, okay, this is not yet very strong. It's of course nice, but it's not very strong. I mean, all these things are conjectures, and they're not theorems. The last conjecture goes back to Johannes Henn mostly, that every Feynman integral at least every Feynman integral that can be written in terms of polylogs, okay? If there is other stuff, then of course we don't know. We don't know what weight means. It's a linear combination. Rational functions as coefficients. Well, algebraic, sorry. Coefficients of integrals of uniform weight. So the expectation by now is that indeed the weight is bounded from above by the loop order. In n equals 4, the bound is saturated. But even in general, you can at least always choose your basis of integrals such that the bound is saturated. And then by chance, in n equals 4, this base is precisely the answer if you want.
Sorry, Claude.
Yeah?
So how do you know in the first place whether your integral falls in the class of functions?
You don't. No, that's what I said. You have to, if you assume that, you don't.
So what's the content of the statement?
The only examples we know are the ones we can compute, fall into that class, and there it holds.
So in practice, you assume that it falls in that class, you try to expand it in this basis of functions, and if you don't find a solution, then you conclude it's just not expressible.
For example, well, you can also, that's something I don't have the time to talk about, you get differential equations for the objects, and then you see if the differential equations fall into the class that lead to this or not. All this should also be, one should be able to generalize it beyond if you go to some mixed Hodge structures, but I think nobody really knows how that works because we have no examples to look at, while we have one. So we have one counterexample that this does not always hold, but when it is this class of functions, these conjectures are fulfilled.
Sorry, just to understand, you wrote algebraic function.
Yeah.
In which sense the polylog is an algebraic function?
No. The integrals are functions of polylogs. What I say is that every integral, the integrals are polylogs. Okay? I say every integral, I can write it as a linear combination of other integrals, so other polylogs. These polylogs will be uniform in weight. So I don't have Lie2 plus Lie3. But the coefficients in front of these integrals, of these classes of polylogs, will be algebraic functions. You will see examples. But basically, I mean, I could have an integral that gives me Lie2 plus Lie3 as an answer. And I can split it up into two integrals. I can find two other basis integrals, each of which has uniform weight, each of which saturates the bound if you want, but I have to put rational coefficients in front. Okay? So the second thing that we can say in general is something called the first entry condition. Well, it's a statement about massless integrals. Well, no massive propagators. And that covers a wide range of applications. Say also n equals 4 super young mills, n equals 8 supergravity, and so on. Then on general grounds, that's Q of t. The Feynman integral has discontinuities, we already said that. But we didn't say where the branch cuts start. Well, discontinuities with branch cut. Starting at points where the scalar products between external momenta are 0. Okay, so the p's are the external momenta. The branch cut starts at the points where the scalar products vanish. So from this I can infer something. Namely, remember that we said the coproduct of an integral is such that the leftmost factor knows the discontinuities. Okay? And now, I take delta of y, that gives me symbolically something like that. Okay? I get two terms. If this is a Feynman integral, the branch cuts all start here. Okay? I is the function of pi dot pj. But we said that it's only the first factor, well, it's the first leftmost factor that knows about the discontinuities. This means that I prime must have the same discontinuities as I. Okay? So this means that the leftmost factor has the same discontinuities. Yeah, as I said, no massive propagators. I think no one really knows the generalization to massive propagators is, but if the propagator is all masses, this is Landau equations translated into this language. So that means that if I go to the symbol, when I iterate it maximally, I only get logs. Okay? When I look at the same symbol of my Feynman integral, I would get a bunch of logs. Let's write them as logs. Okay? I said usually you don't write the logs, but I can if I want to. The symbol would be something like that, symbolically, by a linear combination of terms like that. But the leftmost factor must still have the right discontinuities. So the leftmost factor can only be the logarithm of a Mandelstam invariant. So it's highly constrained. Okay? So the leftmost factor has the discontinuities. The branch cuts start when this thing is 0, so it must be the log of a Mandelstam invariant, pi dot pj. It's highly constraining. Are there questions? This is these are basically the only general statements I can make about amplitudes at this point, but you will see them in action in the examples. Are there questions about this? Okay.
Excuse me.
Yeah.
Can you elaborate a bit on why Feynman integral has discontinuities with branch starting at that point?
There's something called the Landau equations. It goes back to, well, to Landau, so a long time ago. Basically, the statement is that, well, it's a set of equations that give you the branch points. The basic idea is that where do branch points come from? They come from singularities in my integrand. And, well, what are the singularities of a Feynman integral? They're propagators that blow up. Now, so the first condition is, of course, to get a singularity that some propagator satisfies that, or a set of propagators. Masses, yeah. At the same time, that's not sufficient. You know it from the log, because if I have a singularity here and I integrate, then I can always do that. So there's another condition that tells you there are two singularities, and it's quadratic, so there are always two solutions, that pinch the contour. And if you solve that, in the case of massless propagators, you see that the branch points are all located at 0. And your set of equations is what's called the Landau equations. And then you just connect it to the algebraic structure. Okay. So let's look at an example of how far you can go with this. Now I'm now using slides because I'll also use the board a bit to give details, but otherwise formulas become just too heavy to write down. And the example I'm going to discuss is the 4-point correlator in n equals 4 super Young bells. Well, correlator of what? Of the stress tensor multiplied. Okay? So it's a correlator of 4 operators. Now, you know that this, so it's a correlator. Let me write it symbolically like that. Okay? You know that this thing is finite as long as my points are in generic position. But it can develop singularities if the points become light-like separated. Okay? It behaves like 1 over... If the points... Do we have a pointer somewhere? Yeah. So if the points become light-like separated, if xi minus xj squared vanishes, then you have a singularity. You also know that n equals super Young world is conformal. So actually, this function is a function, well, it's a function of the 4 points, x1, x2, x3, x4, but it can only depend on a cross ratio. Up to probably some overall factor that creates the conformal weight, but let's just try to make general statements. Okay? It's a function of cross ratios. You can work them out. There are 6, all possible choices of I, k, j, and l. But there are only 2 that are independent. There's u and v. The other 4, I guess you know, are 1 over u, 1 over v, u over v, and v over u. Okay? So there are 2 independent ones, u and v. And, well, I make a perturbative expansion. I pull out always a factor. So that's this overall factor that carries the conformal weight. So the g's are here are really conformally invariant functions. Well, up to some conformal weight again. Now, what are the g's?
Usually these non-conformally invariant things are in the denominator, not in the...
Well, they are, yeah, sorry, yeah, they are in the g's, sorry. The g's still carry the conformal weight. You will see the definition of the g's is such that they are in the denominator. Sorry, yeah. Because when you write down what the g's are here. Okay? At one loop, the only thing you can have is, well, you have 4 points, x1, x2, x3, x4. And the only thing you can have is you add a 5th point and you connect it and you integrate over it. That's pretty much the only thing you can write down. Okay. So, and indeed, as was just pointed out, and when you look at the conformal weight of this thing, so if you do invert one of the coordinates, if you invert all the points, then you see that this thing still carries a conformal weight, which is precisely captured by this term. Okay. So if you combine the integrals with this prefactor, then they're conformally invariant. At two loops, there's more than one integral, actually. No, there's only one up to rotations, which is this one here. So you have the white points, which are external. You have 2 integration points. And you can show that you only need 2 integrals. You need this one and the one where you rotate by 90 degrees. Yeah. And also this integral, you can easily check it's conformally invariant. Sorry, first of all, do you see these integrals are conformally invariant? Or okay, they're obviously Lorentz invariant, rotation and translation. And then when you invert coordinates, they're also invariant under that. And you can easily check that when you rescale everything, you just pull out a common factor. So they're conformally invariant. Okay, so that's the 2-loop case. Now, these integrals had been computed some time ago by the Yukina, and that's what they are. A bunch of dialogues. So that's what we expect, okay? That's what we say. These integrals, well, there's position space, but then I could also go to momentum space if I wanted to. They're basically some linear combination of logs and dialogues in this case. And you can check that here at L loops, phi L is the loop number, you see that the weight goes up at most to 2L. I get at most lead to L, which is this, okay? For when k is equal to 0, leading term in the Laurent expansion, the weight is maximal and it's 2L. And the other thing you can see is that the arguments of the polylogs are rather complicated. Okay? They're not the cross ratios u and v, but they are x and x bar, which are related to the cross ratios by such nonlinear transformation. It's actually the same as what we had in the very first lecture. Now, if you go to 3 loops, then it was shown by Emery and his collaborators that actually this 3 loops is called it as a combination of 4 integrals. There is now this one here, which is just a generalization of what we had at 2 loops. So these are what's called ladder type integrals. So at one loop, when you go to the dual graph, this is one box, there are 2 boxes. And then there's the generalization now with the third one. So that will be the same function phi. Then there's what is called the tennis court, because when you look at the dual graph, it looks like half of a tennis court. And they found 2 more integrals, which you cannot massage in any way, well, not massage into the ones that you really know, which are these guys here, which are non-planar. So again, the white dots are the external points, the black ones are the integration points, and the dashed lines are numerators. Okay, there are 2. So, this integral is still given by this formula. Okay, L is the number of loops, which is the same as here the number of rungs that was shown by Davidishev and Yukina. So I'm not going to talk too much about this. This was done 20 years ago. Then there is this integral. That one was shown by, again, by Emery and his collaborators, that actually it's roughly the same as this one. Up to some details, these 2 integrals are essentially the same due to conformal invariance. Okay, I just stated here because that's not what I'm interested in, but we can discuss it maybe in the discussion section if you want to know why these 2 objects are the same. So what was missing was this one and this one. So how could I compute these correlators? Well, these integrals that I need for the correlator. And actually the solution is rather nice. So let's look back at what we know. So I said we know the ladder and we know the tennis court. We're missing the other two. The ladder and the tennis court are the same, and they were computed by Devic and Duvsukina. And they found this nice formula where L is number of loops, which is the same as number of rungs. And when you look at it, well, you see it's actually something very simple. It's dilogs and logs. And when you look at the symbol, well, the log will give you log x and log x bar. And the dilogs, if you remember the symbol of the dialog, okay, then you also get 1 minus x and 1 minus x bar from this term here. This, when you look at the formula for the coproduct, it's the Lie1 term. So from this I can conclude that if I compute the symbol of this guy, so when I take the coproduct and iterate it maximally, all the entries will be either x, 1 minus x, x bar, or 1 minus x bar. Okay? Yeah? That's what's sometimes called the alphabet. Okay? It's like a fingerprint of this class of functions. Now, how can I get the other integrals? Well, the idea is now, if I think in terms of the way I presented it, I had only linear algebra. I had vector spaces, and I have relations among my elements in my space, and I conjecturally said that I can resolve all the identities. I know how to get them. So let's basically say, let's construct a basis for the space of functions such that when I iterate them maximally, I get only these entries in the symbol. Okay? That would be my first, it's a guess. I can say, okay, the integrals that I don't know, maybe they still have the same imprint. And I know now what the space of functions is. I know how to find the basis because I know how to resolve all the identities. Let's try to do that. That would be the goal. Okay? Okay, so this is what we had in general, but let me come back to it. It's the first anti-condition again. So now you can actually do better. Because we said, okay, well, these are Feynman integrals. And, well, saying that for a Feynman integral, we said that the first entry must be pi dot pj. When I go back to position space, this means that the first entry is xi minus xj squared. Okay, that's the equivalent of a Mandelstam invariant in position space. So I know that the first entry must be xij squared. That's my first anti-condition, my discontinuities. Okay, I'm trying to say everything I can about the functions that I could get. Now, I know that the function must be conformally invariant. So I cannot have xij squared alone, because that is not a conformal invariant. They must package into something that is u of v. Okay? Tensor something else which I don't know. But I can tell you that if I take the symbol, the first entry is either u or v always. Or rather, I can always rearrange terms such that I get to this form. Because otherwise the function doesn't have the right discontinuities. Okay? And now, I guess I have to stop, and this is actually a good point to stop, because now the magic starts. From here on, mathematicians have solved the problem for us, roughly speaking. But I guess I'm going to tell you this tomorrow.
If not, I guess there have been a number of questions during the course of the talk. So let's thank Claude.